Hey everybody, welcome back to the channel. Today we're talking about roller coasters. We're talking about conservation of energy. We're getting back to our kinetic and potential energy roots. And we're kind of trying to figure out the next step. We've been talking about physics a lot lately. And we actually started talking energy way back in chemistry. Back then we were looking more at thermal types of energy and trying to do things like build hot and cold packs. But now we want to actually try to tackle a roller coaster. So ultimately, if you remember, we had two main definitions of, or classifications of energy. And that was potential and kinetic. Potential and kinetic energy were our big two types. Potential is where we store energy. We have it stored because there's a position going on, or a shape, or a condition. The bonds that we were breaking and the chemicals were releasing energy. You form bonds and store the energy. There's all these things going on with potential energy where we can basically have it stored and ready for use. We even use this during our experiments with the race cars. Kinetic, obviously, is energy of an object's motion. Okay, so kinetic energy is how fast I'm moving, which, again, that links to things like temperature and stuff when you're dealing on the submicroscopic level. But right now, we're dealing with larger objects. We're talking about roller coasters. We're talking about things moving around, people rolling balls, pushing tables, stuff like that. So at this point, really, we're able to look more at physical objects moving around, and that may be a little bit easier for you to understand what's going on. But to go a little bit deeper, energy is the ability to do what we call work. And we haven't talked about work before, but work is actually when a force causes an object to move. And the energy is what allows there to be a force, realistically. So if you are pushing an object, you are using energy to create a change and an acceleration in your environment. So that's kind of a big difference from what we were looking at before, because we didn't have the concepts of forces that we had discussed previously. So now we get a little bit more of the energy puzzle revealed to us. And work is literally force times distance. So the amount of work done is the force times the distance. So ultimately, potential and kinetic energy, there's a lot of stuff going on. And if you think about it a bit, we spend the majority of this class actually discussing energy in one form or another. Elastic potential energy, you saw in the rubber band race cars. Chemical potential energy you saw inside our chemistry experiments, making the hot and cold packs. This particular exercise that we're about to do, the roller coasters, uses gravitational potential energy, which is much more common in kinetic and potential energy discussions. We've looked at thermal energy, which is a form of kinetic. We are about to do mechanical. We will be exploring electrical engineering energy when we start making electromagnets. Acoustic energy when we do the robot music stuff, lights, when we start talking about like waves and things. So a lot of the stuff we get into with waves, it's all about energy. Realistically, energy kind of ties together as a big theme my entire year with you. And that's kind of cool. And actually, energy runs through a lot of science in general. It's what they call a cross-cutting principle. Cross-cutting concepts. All right, so that all said, let's talk about roller coasters. So a roller coaster is like kind of this giant engine of physics. It's really the physics of work and energy all played out. So in general, when you're looking at a roller coaster, you start off and there's some sort of a motor or and a chain usually that like pulls you up to like this really high hill. And that hill is generally the highest hill in the roller coaster, and that's kind of important to understand. That the first hill is the highest is actually really important, and you may not realize why. But that has to do with it's literally setting the amount of potential energy inside the system of the roller coaster. Okay, so you have this massive hill that we start out on top of, and we use the energy that we got from our position to then go through the rest of the ride. Okay, so really there's an investment of energy in that beginning where the motor is literally building potential energy and storing it in the position of the car before it releases that energy and you zoom through the ride. Okay, so ultimately, if you remember correctly, when we talked about energy, we talked about something called conservation of energy. And a roller coaster can conserve energy if it were frictionless. Okay? So if you remember, energy can't be created or destroyed. It only changes forms. So if you start out with a bunch of potential energy, you can turn that potential energy into kinetic. Okay? You can turn being on top of a hill to going down the hill real fast and then restore that energy back into potential by going back up into a loop or a hill or whatever. Okay? Literally, you're transforming the potential and the kinetic energy back and forth to make an entertainment ride, is literally what we're doing with these sort of things. Now, when we talk about it, we talk about this idea of a total energy. Okay? The total energy of a roller coaster is its potential plus its kinetic at any given point. Okay? Now, at the very top of the roller coaster is a really key point because it's got the most potential energy. Okay? You have the most potential energy at the top of the roller coaster at the very first hill. That's where all the potential energy is max and there's no motion yet because you haven't fallen yet. So in that split second, at the very top of the roller coaster, you are zero kinetic and max potential, and the total mechanical energy is just potential. It's really just your mass of the roller coaster car and you and everything times gravity, which is 9.8 meters per second squared, times the height of that particular hill. All the energy is going to be that. And that's going to be something we're going to use a lot. But as you go through the rest of the ride, the amount of potential and kinetic keeps shifting as you're going through it. It's an exchange between potential and kinetic over and over and over again. And that number always stays the constant, always stays the same as the total energy. Okay? The total energy of the system never changes. Except that friction exists. So obviously we don't live in a perfect, idealistic, frictionless environment. We live in, the real world, and there is imperfections in the system. There's going to be friction. There's going to be heat loss due to that friction. You're not going to get to keep all the energy all the time. And that's actually the real trick when it comes to building your own roller coaster, is that you're going to lose a good amount of energy as the cycle progresses. And that is really important in how you design what you're making. So ultimately, a roller coaster is just a giant engine of energy exchange. Okay? At the top of the hill, you have all gravitational potential energy. There's no kinetic at all. So at the very top of that first hill, you are 100% gravitational potential energy. That is your total energy. The easiest way to find the total energy of a roller coaster is to look at the first hill. Okay? Which again is mass times your gravity times height. Gravity 9.8 meters per second squared. Now at the bottom of that hill, if you were to go down all the way to the bottom, you'd have no potential energy. The whole thing would be converted to kinetic, which is 1/2 mass times velocity squared. And ultimately, what we're doing as we go through the roller coasters, we're exchanging energy between that height. So as I go up, right, I have more potential, less kinetic. As I go down, I have more kinetic, less potential. That's the idea. Okay. Ultimately, you want to remember that the total mechanical energy remains constant across the whole thing. Okay, that's the key concept, is that by setting the energy on that first hill, you set the energy for the entire roller coaster. Realistically, you can never go as high as that first hill again because all the energy comes from that. And ultimately, your roller coaster can never go higher than the first hill. That's really important. That's a question that comes up sometimes. And keep in mind, real roller coasters aren't frictionless. Real roller coasters aren't going to conserve the energy properly. We only consider the energy conserved inside physics problems when we're doing these kinds of things. And that's really because there's no way to account for the friction and stuff with the math we use. You would have to go very, very far in college to get to where you see stuff like that. So don't worry about those pieces. Just understand that in a real system like the one you're going to be building, energy is not going to be properly conserved. You are going to lose energy over time. And realistically, the answer is make your hills shorter, guys. Make your hills shorter and it'll work. If you try to make your hills and your loops really, really big, you'll find that it doesn't work so hot. All right. So, obviously, we're not just building roller coasters. We need to be able to solve these roller coaster energy problems. So, let's talk about some of the details here as we go into some examples. So, the total energy is equal to the potential plus the kinetic. Your potential energy is going to be mass times gravity times height. Potential energy is always mgh, mass, gravity, height. Kinetic energy, on the other hand, is 1/2 mv squared, 1/2 mass times velocity squared. So depending upon which one you're looking at, you're going to use either of those equations. You could also say the total energy is equal to mgh plus 1/2 mv squared. Okay, substituting for both. Always start out a roller coaster problem by solving for the top. So solve for your first hill. That's going to tell you how much energy you have total. Okay, it's really easy to solve for the first hill because kinetic is 0 and potential is everything. So the total energy equals the potential energy of the first hill. And then once you've dealt with that, you calculate the energy at any given point by calculating the potential and subtracting it off of the total. So if you want to look at any given height, you just calculate that potential energy, okay? Once you calculate that potential, which is easy, it's mass times gravity times the height. You subtract that off of the energy of the top of the highest hill, and that gives you the remaining energy. The remaining energy must equal 1/2 mv squared, so you just work that out. And you do have to do a square root, most likely. And that's going to give you your velocity at any point, realistically. So velocity can always be calculated when kinetic energy is known because it's 1/2 mv squared. Very, very easy. All right, so let's take a look at one of these problems here. We got a roller coaster. We got a few points. Notice I got points A, B, C, and D. And I got a bunch of measurements for how high things are. Notice that point A is 140 meters up, point B 95, and between C and D there, it looks like it's a constant at 80 meters. Okay, we're told a 350 kilogram roller coaster cart is released from rest at point A. Ignore friction and air resistance. Calculate the kinetic and potential energy at points B and C. All right, well, point A is going to tell me the total energy. And we know that it's at rest. We know that it's 350 kilograms when it's 140 meters up. And potential energy is mass times gravity times height. So because kinetic energy is 0, the total energy must equal the mass times the gravity and the height at the highest hill. All right, Well, let's plug it in. 350 kilograms times 9.8 meters per second squared times 140 meters. All right, plug that into my calculator and I find that the total energy is 480,200 joules. A joule is really small, guys. Joules are very small, and as a result, you're going to see numbers that are really, really big when you're doing energy calculations like this, because we're dealing with a roller coaster system. We would expect numbers that are pretty large. We aren't just talking about like the 1 kilogram object being pushed around a desk anymore. Okay, we're talking about big, big, big systems here. So I found 480,200 joules. That's the total energy of the entire system. This thing's frictionless. So at any given point on here, whether it be the ones that are labeled or any other point, you have 480,200 total joules. If you added the potential and the kinetic together, it's always going to equal 480,200. Okay. So point B here tells me that it's 95 meters up. It's really easy to calculate potential. It's a little bit harder to calculate kinetic. So what I'm going to do is I'm going to tackle the potential, subtract it off my 480,200, and then I can solve for my kinetic. So potential energy is mgh. 350 times 9.8 times 95 in here gives me 325,850 joules. Again, you're dealing with big numbers because we're talking about roller coasters. I'm going to subtract my potential off of my total, and that's going to give me the remaining energy, which is all kinetic. That's 154,350 joules. That equals 1/2 mv squared, mass times velocity squared. So because I'm not being asked to find velocity or anything, I'm actually done with the problem right there. That's actually the energy at point B. Point C here is 80 meters. We know that potential energy is mgh once again. We're going to multiply out 350, my mass of my object, 9.8, the acceleration due to gravity, and 80 meters this time is my height. I get 274,400 joules. I subtract that off of the total energy, and it tells me my kinetic. 250,800 joules. That's all there is to it. So finding energy on one of these things is actually super duper easy. It's barely an inconvenience, really. You're just doing the same problem over and over again. The real trick is to understand that the total is equal to the potential plus the kinetic. Now, let's say that I actually wanted to tackle the velocity question. Okay? What if I wanted to not just find energy, but I wanted to find the velocity at that point? Okay, so here I'm asking a slightly different question, but check it. I actually don't need to know the mass of the car to solve these. When I start at the top of a roller coaster, all my energy is potential. That means my total energy is mass times gravity times the initial height. So the total energy is equal to mass, gravity, initial height, or h sub I, as I've labeled it here. Now, that's the total energy of the roller coaster. Okay? Now, the energy at any point would still be the same. The total energy stays the same, but it's going to be equal to mass times gravity times the height at whatever place I'm at, plus 1/2 mass times velocity squared. So if you substitute everything in, use all the substitution stuff that we talked about back in January, I could make an equation here that says, well, total energy is mghi, and it's mghf plus 1/2 mv squared. Notice that every single term there has a mass in it. Every single term there has mass, which means I could divide by mass through the whole equation and cancel it out. And that's what I'm going to do. I'm going to cancel mass from every single term in this equation. And when I do, I get a different equation that won't have mass in it. Mass literally won't affect the velocity. It doesn't matter if it's a 100 kilogram cart or a 500 kilogram cart. It's going to be the same velocities. So at any given point, velocity can actually be found with this equation below. I simplified it out for you. I got rid of all the masses and I've rewrote it so velocity is solved. Okay, don't worry about how to get there. It's a lot of math and might mess you up a little bit to see it. If you're really interested, come by and I'll show you at any time. It's actually pretty easy to do, but I just don't want to confuse people who are a little bit weaker on the math side. But the answer really ends up coming to be that velocity is equal to the square root of 2 times gravity times the difference of the heights. That equation right there would give you velocity at any point without needing to worry about the math. You just need to know the height you started at, the height you are currently interested in, and that's it. Those 2 pieces of information will give you the velocity of the roller coaster at any point. So let's take a look here at this particular roller coaster problem. We got 35 meters up to get to point 1. Point 2 there appears to be the bottom of the hill. We got 28 meters up for point 3, and we got 15 meters up for point 4. So the roller coaster's been dragged to point 1. It was at rest, and we want to calculate its speed. We want to know the velocity at points 2, 3, and 4. All right, cool. Well, at point 2, I'm going to use my equation here. I know the velocity is the square root of 2 times gravity times the difference in the heights. Well, the difference in the height is 35 minus 0. So I go ahead and plug that all in, multiply it out, and I hit the square root button for square root of 686 to find this 26.2 meters per second. Okay. The initial height here was 35, and I went down to my 0 point, presumably, in this picture, because we have no real understanding of what's at 2. So this would be 35 minus 0. But now, I'm going up to 28. So keep in mind, my initial height was 35, so now this equation is going to be a little more interesting. I have 35 minus 28 inside the height differential there. So 2 times 9.8 times 35 minus 28 there. Well, 35 minus 28, I do my parentheses first. That gives me 7. 7 times 9.8 times 2 is what I'm looking at, which is 137.2. You square root that, and you get 11.7 meters per second is the velocity at point 3. Point 4, pretty much the exact same thing. Except now we're talking about 35 minus 15. So we got 20 inside the parentheses there. We multiply it all out, and you get square root 392, which is 19.8 meters per second. And that's really it, guys. Those are the 2 types of problems I can toss at you about roller coasters. I can ask you about the energy at any point in the roller coaster. I can ask you about the velocity at any point in the roller coaster. And ultimately, those are how you solve the problems. You apply the equations I've shown you. You're going to have this. Ed puzzle here for the entire time. You can always have these equations up on the board when you're doing the problems and stuff. So realistically, you're going to see this inside your lab. You're going to see this inside practice problems, and it's really not that hard, guys. If you need to go back through this video to see how to do the calculations again, I highly recommend you do that. And overall, I hope you guys have a great night, and I'll see you in class tomorrow.